Welcome back. So, where we are in the course is that we're in the process of working out dynamics using rate equations. I've sometimes advertised this section as having to do with chemical transformation on the grounds that the macromolecules of cells undergo transformation. We might put on a phosphate group onto a protein, or we might convert some substrate into some product. Each of these is a case of chemical transformation. And the thing that I want to do now is take what might ostensibly appear to be a big detour. And the reason is I need to introduce the theory of statistical mechanics. And the reason for that is that we now need to have a little bit more finesse as we handle binding problems. And you'll recall that we did the example of a ligand receptor kinetics in a previous vignette, and that was fine. We kind of knew how to write down, dLr by dt, and we said, well, that had a minus sign with a k off, and then that was proportional to how many candidates there were to decay, and then we had an on rate with L times R. And what I want to do now is I want to handle some more subtle examples. And just to give you an example, I want to be able to do problems such as, here I have two genes, and this gene over here produces a red protein which binds over here and represses it, and this gene produces a protein that's green, and it binds over there and it represses it. Actually, I should probably use the proper notation for this, which is this guy comes over here and represses, and this guy comes over here and represses. So I'm going to use this symbol with the sort of flat arrow as my way of representing repression. So let me annotate that. So this refers to repression. And the kind of thing that we're going to want to do, so let's call this guy R1, repressor 1, and this one R2. And the sort of thing that we're going to want to do is we're going to want to write down the dynamics of R1 and R2, and we'll acknowledge that R1 as a protein can degrade, but there'll also be some rate at which R1 is synthesized, and that will be inversely dependent on how much of R2 there is, for example. So right now I'm merely asserting. I'm not explaining. I'm just telling you that we're going to be interested in cases where we will want to write down these sorts of coupled equations, and the part that I'm trying to motivate right now is this function that I show right here, or this function. And these are functions that represent cooperative binding and repression. If you look at this, you'll see when R1 gets large, when R2 gets large in this case, here, when R2 gets large, the amount of production of R1 goes down. In this case, when R1 gets big, the production of R2 goes down. And the thing I need to do is I need to give you a theory of these kinds of terms. In other words, I don't want to pull them out of thin air. I want to motivate them on the basis of things that we know about binding, about the interactions between proteins and DNA, for example. And I can think of a whole host of examples like this where I need to be able to write down rate equations, but the kinetics is the right-hand side of these kinetic equations is going to be richer than what we've written down thus far in our sort of simple mass action kinetics of the variety that I did when I wrote down the dynamics, for example, of ligand receptor binding. Okay, so the point is the detour that we're on now, or the sort of aside, is we want to do an examination of the tenets of statistical mechanics, and the reason for that is that statistical mechanics is the theory that tells us how to reason about situations like the binding of proteins to DNA or the binding of proteins to ligands but in sort of complicated scenarios. So that's what the aside is about. The aside being, a couple of vignettes here in the middle of our dynamics section, but these vignettes are going to focus on statistical mechanics. I'm not sure what happened, but hopefully I'll recover the screen again. Maybe this was my doing. I'm not sure. Just bear with me for a sec. I'm really sorry. I seem to, depending on where I am, and I mean which building I'm in and what internet I have, I sometimes seem to lose my connection between my iPad and my computer. Anyway, seems like we're back. So statistical mechanics. All right. So statistical mechanics, the general domain of inquiry of statistical mechanics is it's a theory. So it's the theory that produces or computes the probabilities of what I'm going to call microstates. This may seem like a mouthful with a bunch of jargon in it, but let me give you an example. Wherever you are, you're sitting in a room and you're breathing the air. So look around you. You're surrounded by all these molecules, and each molecule could be at a certain position, and it could be moving at a certain speed. And it's insanity to imagine writing down a list that has the XYZ coordinates and the XYZ components of velocity or momentum for each and every one of the 10 to the 28th molecules that are in this room. And so rather than trying to enumerate in sort of a deterministic fashion, according to what we sometimes refer to as Laplace's demon, this demon, if it had a perfect knowledge of the world, it would basically be able to, from an initial condition, predict all the way out into the future what the system would do. But that's not the situation with the molecules in this room. So what we do instead is we abandon the idea of certain knowledge of the position and velocity of every molecule, and instead we say to ourselves, let's actually think about the probability that a molecule will be here, a probability the molecule will be there, the probability of it going this fast or that fast. So that's what I mean when I talk about the theory that produces the probabilities of microstates. And I think it's a very interesting question for you, the listeners, to think about, and that is the status of what we might call laws of nature, I'm gonna call them laws of nature. So where do they come from? Where does F equals ma come from? Where does the four Maxwell equations come from? Do they come from some deeper thing, or do we accept them as articles of faith or some assumptions, fundamental assumptions, and then we explore their consequences? And it's that latter point of view that I'm going to take here, even though I accept that, under some other set of assumptions, I might be able to derive, for example, a law of motion. But for my purposes, I'm going to say that laws of nature are a reflection of our experience. We go out into the world, we observe the world, we find that there are certain regularities, and we write down our sense of those regularities in mathematical form. And one of those is this law of the Boltzmann distribution, which tells me the probability of finding my system in a state whose energy is E sub I. So I'm going to label my states with an index I, and the probability of finding the system in a state where it has energy E sub I is given by this expression, which tells us it goes like the exponential of the energy of that state divided by kBt, where kBt is exactly what I wrote down the other day, and that is the thermal energy. So it's 4.1 piconewton nanometers. And I think, as I said the other day, this is the natural energy units of physical biology. It tells us about the confluence of this deterministic energies of the cell associated with things like molecular motors, and then the constant thermal jostling due to the collisions of the surrounding medium. And we know about that in the form of things like this, which is, if I take my Eppendorf tube, and let's say it's at 37 degrees, and I put it in the ocean, What will happen after some amount of time is that because of the collisions between the molecules of the water and the Eppendorf tube, and then the Eppendorf tube with the water inside of it or the solution inside of it, the system will equilibrate. And when I say equilibrate, what I mean is that we'll more fairly partition. When we start out, there's more energy inside of the tube than out, in the sense on a per molecule basis. The energy is not partitioned fairly. And so what Boltzmann's distribution tells us about is, in a way, the energetics of fair partitioning. So we're going to try to invoke this principle, and we're going to adopt the kind of language that I've already been using throughout the various vignettes, and that's the language of protocols. And now, what I mean when I talk about the statistical mechanics protocol, I want you to actually think that there's an algorithm. Now, that is not to say that there's not some deep science behind the origins of that algorithm, but for my purposes, in this course right now, where I have practical objectives, which is I want to compute certain binding probabilities, I don't want to talk about the niceties of where it comes from. I would like to talk about that later, and if you look at our book, you'll find that we discuss where Boltzmann comes from 4 different perspectives. But for my purpose, I'm going to say, let's accept that there's this law called the Boltzmann probability law, and then let's use it. So how do we use it? We follow these 4 steps. The first thing we do is we identify the relevant states or configurations, and here I'm going to use the example of an ion channel as a window onto the more general prospect of using the Boltzmann distribution. So I only have 2 states for my model ion channel, the open state shown on the top and the closed state shown on the bottom. So I have identified the relevant states here, open and closed. Next thing I do is I find the energies of those states. So I expect that the energy of the closed state is going to be lower than the energy of the open state. That is to say that I expect, in general, to find the channel in the closed state. Then this is going to seem a little obscure for the moment because it doesn't really apply in the ion channel case particularly, but we compute the multiplicities. What I mean by that is the number of different ways of realizing the particular microstate. And let me just give you an indication of what I mean by that. So here, these are all microstates that have the same energy. There's a certain number of particles. They're in solution. Their energy is the number of ligands times the energy of a single molecule in solution. And each one of these states, it has the same energy, but there's many different ways of putting my L ligands on my omega lattice sites. That's what I mean by the multiplicity. Here's another example. So for DNA on a surface, there's many different states. Each one of these realizations is a different microstate, and some of them may have the same energy, and I want to count. That's what I mean by multiplicity. I want to count the frequency or the number of times that I have a given microstate. And then the final point is I compute the Boltzmann weights as the multiplicity, which we got in step 3, times e to the minus energy, which we had in step 2. And this tells us then the relative probabilities of the different microscopic states of interest. So for example, now if I wanted to compute the probability of being open, I do the probability the way I always do it. And that is to say, in the numerator I put the thing that I want the probability of, and in the denominator I put the sum over all the things that could happen. So the scenario is the same all the time. Numerator is the thing we want the probability of. It has a certain statistical weight, which I got here, and then the denominator is the sum of all of the possible outcomes and their statistical weights. And so that gives me an open probability, and this expression is an expression which is used regularly in the literature of ion channels. If you go look, for example, at the paper of Perozzo from maybe 2002 on the mechanosensitive channel, MSCL, it's a very beautiful paper, one of these experiments to change your life for type of papers. If you look at the caption, you'll see that when they write down the probability curve, it's exactly of this form that I'm showing you here, and that's the result of statistical mechanics. So, what do I want to review, or what do I want to say? I'm saying that we're interested now in a theory of statistical mechanics. This first vignette is in a way to get to know about as opposed to know. We're going to have to do some actual calculations to get a little bit more intimate with the underpinnings of how this thing works. But this is just to get you acquainted with the idea. There's a law of nature, I'm going to call it, which is this notion of the Boltzmann probability, the Boltzmann statistical weight. The idea is very simple, and I showed it to you in this fundamental equation. So I just am saying if I want to know the probability of a given state, I find its energy and I exponentiate it. And the energy scale is normalized by KBT. KBT tells me how much thermal energy I'm allowed to give to my system so that it can do something interesting. If we were in the classroom right now, I think I would likely try an example on you, which is that I would try to levitate. So what do I mean by that? I would sit on the floor and I'd close my eyes and sit in some yoga position, and then I'd tell you, okay, well, let's see if I can levitate by a micron. And the way that I would go about that is I would say, well, let's compute the probability that I'm at a height of 1 micron and divide it by the probability that I'll be at a height of 0 microns. So the edict from Boltzmann is that I take e to the minus the energy of the state of interest and divide by KBT. So what am I writing here? So I'm writing this part right here is my potential energy if I have levitated to a height h. So let's look at the case where I levitate by a height 1 micron. So this is for me. We're going to take my mass, which is 100 kilograms. I know that g is 10 meters per second squared, and my height is going to be 10 to the minus 6 meters. And then the denominator here is 4 times 10 to the minus 21 joules. The numerator has units of joules as well. This thing is dimensionless, okay? So what I find is that I have 1/4, and then I have 1,000 upstairs, 10 to the 3 times 10 to the minus 6. So that gives me a 10 to the minus 3, and then a 10 to the 21. So this gives me 10 to the 18th divided by 4. And so the probability of me levitating to a height h is given by e to the minus 10 to the 18th over 4. In other words, I'm not going to levitate. But if we were to think about the levitation of a bacterium, then what would happen is that instead of having here a mass of 100 kilograms, I would have a mass of 10 to the minus 15. So I'd have a 17 orders of magnitude switch. So for a bacterium, m is of order 10 to the minus 15 kilograms. And so the probability of levitation in this case is e to the minus, and then I'm going to get 10 over 4. So, answer is reasonable. There's a probability. And, I always like to say every laboratory has an anti-Boltzmann device, which is called a centrifuge. And here I did this in air. If we'd done this in water, it would have been the buoyant mass, and it would have been even more likely that we would have seen levitation. So let me just see if I have any other key things that I wanted to point out. I think that's really the main points that I wanted to make as by way of introduction to statistical mechanics. Maybe let's call it a feeling for statistical mechanics.